I have modeled a scenario where a projectile is launched with an initial velocity of 30 meters per second. The motion of this projectile is governed by two forces, one being the gravitational force, g meters per second caret 2, and the other being a force dependent on velocity, represented by the constant k times the velocity. Initially, we set k to 0, indicating that we are disregarding any wind resistance. In this case, the only force acting on the projectile is gravity. As a result, the upward and downward motions exhibit symmetrical behavior. At any given vertical position, the velocity of the projectile is the same, regardless of whether it is moving upward or downward. The velocity graph, representing the projectile's velocity over time, displays a linear pattern. During the upward motion, the velocity steadily decreases from the initial 30 meters per second, reaching 0 at its peak. Conversely, during the downward motion, the velocity increases linearly, and upon reaching the ground, it becomes minus 30 meters per second. This symmetry and linear behavior illustrate the simple dynamics of a projectile under the influence of gravitational force alone, providing insights into its motion in the absence of wind resistance. Now in this scenario, a projectile is launched with an initial velocity of 30 meters per second. The motion of the projectile is influenced by two forces, the force of gravity, g meters per second caret 2, and another force that is proportional to its velocity, denoted by k times v. For this explanation, let's set the value of k to 5, indicating that we are now considering the impact of wind resistance. In this case, the projectile experiences the combined effects of gravity and wind resistance. Consequently, the upward and downward motions no longer exhibit the same velocity at corresponding vertical positions. The symmetry observed earlier is disrupted. Examining the velocity graph, we observe a nonlinear curve. Unlike the linear pattern seen in the absence of wind resistance, the velocity graph now shows curvature. Notably, the velocity reaches a saturation point at minus 1.96 meters per second during the downward motion, indicating a terminal velocity. During the upward motion, the velocity starts at the initial 30 meters per second and gradually decreases. However, in the downward direction, the velocity curve shows a more prolonged descent, reaching the terminal velocity of minus 1.96 meters per second. This asymmetry in velocity and the presence of a terminal velocity demonstrate that the downward motion, influenced by both gravity and wind resistance, takes more time compared to the upward motion. Furthermore, it's evident that the upward motion takes less time compared to the downward direction. This asymmetry in the time taken can be attributed to the opposing forces acting during the downward motion. In this phase, the force of wind resistance acts against the motion, resisting the acceleration due to gravity. While gravity attempts to accelerate the projectile downward, wind resistance counteracts this force. Conversely, during the upward motion, both gravity and wind resistance work together to decelerate the projectile. As it moves against the gravitational force, wind resistance contributes to the overall deceleration, resulting in a quicker ascent. In summary, the interplay between gravitational force and wind resistance introduces a dynamic element to the projectile's motion, influencing both its velocity and the time taken for upward and downward movements. This script models the motion of a projectile launched with an initial velocity of 30 meters per second. The projectile is influenced by gravitational force, g meters per second caret 2, and a velocity-dependent force, k times velocity. Key components. Constants, g, gravity, k, proportional constant. Initial conditions, initial velocity and position. Projectile, a visual representation using a blue sphere. Graphs, visualization of time versus position and time versus velocity. Simulation details. 1. The script uses vpython for 3D visualization and animation. 2. Time-related parameters are set, including the time step, dt, and initial time, t. 3. 2 graphs are created to show the projectile's position and velocity over time. 4. The main loop simulates the projectile's motion until it reaches the ground, y-coordinate is less than 0. 5. Forces, including gravitational and velocity-dependent forces, are calculated. 6. Net force is determined, and velocity and position are updated based on the laws of motion. 7. Time, position, and velocity information are displayed and updated on the graphs.